Hello and welcome to a new video in the Basics of Cryptology series on the Cryptography for Everybody YouTube channel. Today you will learn what padding with block ciphers is. We structured the video into 7 different parts. In the first part you will learn what the term padding means. And then we will have a look at different ways to apply padding to block ciphers. And after that, of course, we will have a look how to use padding with AES, DES in CrypTool 2. But before we start, we have a look at this slide here that you probably know from all the other videos of this series. And as we know, cryptography is the art of making ciphers and cryptanalysis is the art of breaking ciphers. And in today's video, we have a look at cryptology, cryptography, modern cryptography, symmetric modern cryptography. What is padding? Before we discuss what padding actually is, we first need to know what a block cipher is. If you're a viewer of this channel, then you probably already know this, but we have here a small recapitulation what block ciphers are. And block ciphers encrypt blocks of data of the same size. And for example, AES works with 16-byte blocks and DES works with 8-byte blocks. And how does this look like? We have our block cipher here as a box, and then every time we encrypt, we put block size bytes of plain text into the block cipher. Of course, we need the key, and then block size bytes ciphertext come out of the block. And when we want to encrypt more than block size bytes, of course we have to repeat this process. And in the previous video we had a look at modes of operation for block ciphers. And now we have a problem. What do we have to do when the last plaintext block is not exactly block size bytes? For instance, we only want to encrypt in the last block 14 bytes instead of 16 bytes with DES. And the solution to this problem is padding. And padding adds data to the end of the message prior to the encryption. And it does this by defined algorithms, which we call padding algorithms. And we have bit padding and byte padding. And here in this video, we only focus on byte padding. If you want to know more about bit padding or about padding in general, I highly suggest that you have a look at the really nice Wikipedia article on padding in cryptography. And here's one hint. Padding was also used with some classical ciphers in history, and it is used today with asymmetric cryptography also. For example, the optimal asymmetric encryption padding, or abbreviated OAEP, is also applied to the RSA algorithm. Now let's have a look at our first padding mode, and our first padding is no padding at all. What does this mean? We have an example here. We have a plain text input, for instance, for the AES with 16 bytes. And here these Ds stand for data bytes. So we have 16 bytes data. And the last block then with this mode, if you call this a mode, has always to be of block size bytes. And yeah, that's a problem because advantages we have none with this mode, but disadvantages we have a few. First of all, the application or user which uses or who uses the block cipher, the AES in our case, has always to provide block size bytes in the last block. So you cannot encrypt less bytes in the last block than 16 bytes. You always have to take care that your application has 16 bytes in the case of AES in the last block. And the cipher does not accept blocks which are smaller. For instance, our CrypTool 2 shows an error if you select no padding at all and you want to encrypt fewer than 16 bytes with the AES. Now let's have a look at the first real padding mode. And the zero padding mode adds 0 bytes to the end of the last block until we have block size bytes. And if the last block is already of block size bytes, it does nothing. Here we have an example again. We have a plain text input, for instance, AES 16 bytes, and we have a non-complete block here. These Ds stand for data bytes, and with this padding, we add 0 bytes to the block at the end. Advantages of this mode is it's easy to implement, so you just add 0 bytes to the end of your data, but there are some disadvantages. The first disadvantage is that zeros that are actual data at the end are also removed. let's think that this D byte here is also a 0. When we decipher or decrypt a received block or the last received block, then this padding mode would also remove this D here. And then in our application we could have a problem. So in our application, or the user has to store how many bytes of the last block are actual data, so that we know when we get less data in the last block that we have to again append the missing 0 bytes of the plaintext block. Now let's have a look at the 1-0 padding. And the 1-0 padding adds a 1 byte and then it fills the remaining parts with 0 bytes until we have block size bytes. And if the last block is already of block size bytes, we add an additional block. Here we have again an example. We have some data, and then after the data we add a 1. So this is exactly a byte containing the value 1, and then we fill the remaining part with zeros. And when we want to decrypt, we decrypt the last block, and then we remove zeros from the end until we reach the 1. And if we have a complete block of data, then the 1 would stand at the beginning of the last block and we only had zeros here. Advantages are that this is also easy to implement and that no data can get lost at the end compared to the 0 padding. Disadvantages are short blocks with only a few bytes of data have a lot of padded data that we know. So let's think of we only have 1 byte, then we would know the remaining part of the block already, since it's really clearly defined what we have here. We would have a 1 and then only zeros. Now let's have a look at the ANSI X923 padding. And this padding adds 0 bytes to the end of the last block until we have block size minus 1 bytes. And it adds the total size of added bytes as a single byte value to the end of the block. And if the last block is already of block size bytes, add an additional block. Here's an example again. Let's think of we have these D data bytes, then we add zeros after these, and then we count how many bytes we padded. In our case, this is 1, 2, 3, 4, 5, 6. So we add the 6 here. So when we decrypt this last block, we just have a look at the last byte. We see here the 6 and we know we have to remove 6 bytes from the decrypted data. Advantages are this is also easy to implement and also no data can get lost at the end compared to 0 padding. Disadvantages are that short blocks with only a few bytes of data have a lot of padded data we know. So when we only have 1 byte, we already know 15 remaining bytes of this plaintext block. And some implementations also add random bytes here at the 0 positions instead of 0 bytes. Now let's have a look at the ISO 10126 padding. And in this mode, we add random bytes to the end of the last block until we have block size minus 1 bytes. Remember, in the last mode, this was also done with some implementations. And we add the total size of added bytes as a single byte value to the end of the block here. And if the last block is already block size bytes, add an additional block. And here is an example. We again have a few data bytes. We add random bytes at the end until we reach the byte value before the last byte. And here we write how many bytes we added. In our case, we have again 1, 2, 3, 4, 5, 6. This should be 4 and 5 here. Advantages are that this mode is also easy to implement. No data can get lost at the end compared to 0 padding. And instead of padding with known data, for instance with the 0 bytes padding, we now pad with random data. And we have no disadvantages compared to the other modes. Now let's have a look at PKCS padding. And here we add size bytes to the end of the last block until we have block size bytes. What does this mean? In our example again, we have a few data and then we count how many blocks, how many bytes we have to pad. We count 1, 2, 3, 4, 5, 6 and we just add 6 to the end of the block as many times as we have the 6 here. So 6 times 6. 1, 2, 3, 4, 5, 6. 6 times 6. If we would have only 5 empty bytes or missing bytes, you could say here we would write 5, 5, 5, 5. 5, and then with 4, 4, 4, 4, 4, 3, 3, 3, 2, 2, or 1 if we have this here. The advantages of this mode is it's also easy to implement and no data can get lost at the end compared to the zero padding. Disadvantages are that short blocks with only a few bytes of data have a lot of padded data again that we know. Now that we know all the padding procedures or modes that we also have implemented in CrypTool 2, let's have a look at padding of block ciphers in CrypTool 2. And I'm here now in the Start Center of CrypTool 2, and I want to show you the different padding modes that we have implemented, for instance with the AES. And to do so, this time we create a new workspace. In the workspace, we want to have the AES cipher. Then we need a text input for our plain text for testing. This is plain text. Then we need a key. And of course, we want to have a ciphertext. And in this case, I want to have the same width and the same height as with our plain text. And this here is our ciphertext. Then we want to convert from the string here using the string decoder to CrypTool stream here. And I want to enter hexadecimal values. So I change the string decoder here to hex. We can copy this string decoder for our key, since our key has to be a byte array. Let's connect this to a key. And I will omit the initialization vector. I will also use a chaining mode here, which doesn't need an IV, an initialization vector. This is electronic codebook mode, just for demonstration purposes. Then we need also a converter here, an encoder. And we want to see here also hex data. Change the string encoder to hex. Now I want to also decrypt what we have done here. So we copy the AES, change it here to decrypt, then electronic codebook mode, padding none, because we want to see what the padding mode does. When you change the padding to none, so you first encrypt using a padding and then you decrypt using no padding at all, you will just see the padded byte since the AES won't remove it. Then we want to have here our plain text. And we connect this. And we have to connect the key. And for the key, we just need 16 bytes. I will just set the key to 16 times 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we can also make this a little smaller and put this here. So, and then a line left and a line right. Yeah, this looks nice. Okay, so what do we have here? We have a plain text input, and as a text input where we can enter plain text. This is converted to a CrypTool stream here, and we set the encoders and decoders all. I hope we did this to hexadecimal. Yes, all these are set to hexadecimal. So we encrypt using the AES, and we will encrypt only a single block using padding mode, and we will have a look at all the different padding modes, and then we decrypt to see what this padding mode actually does. So let's start with no padding at all. So when we have no padding at all and we only want to encrypt a single byte, then of course we get an error because AES works on 16 bytes. Block size of 16. So I just copy the key here. I know this is 16 bytes. Let's encrypt it. So AES encrypts it and then AES decrypts it back. And yeah, as I said, with no padding at all, if I want to encrypt fewer bytes in the last block, and since we only have one block here, it's the last block, we get an error. So let's remove all the bytes despite this, and I will change this to FF so that we can better see which byte here is the byte that we added. Now let's change it to the next mode, and this is zeros. So when we press play here, we can see it obviously padded because we get a complete block here and it could encrypt this block. And when we decrypt it without using any mode, we can see that it added with the zero, with the padding mode here, only zeros, it added zeros until we have a complete block. Now when we change the second AES also to zeros, we only get, okay, this is a bug. It should remove the zeros until we have only FF here. I don't know why it does this. Encrypt, decrypt. Okay, let's have a look at the next modes. Probably this is a bug that I have to fix. Then the next mode is PKCS7, and we change this again to none. Let's press play. So with PKCS7, we can see that it adds 0f to the end of our plaintext here. And this is because we have 15 bytes that are missing at the last block because we have only 1 byte and we have a 16-byte block. And in this case, it adds 15 times 15. If we add an additional byte here, we have 14 times 14, of course, as hex values here. Okay, let's have a look if we can successfully decrypt using PKCS7. Press play, and here it works. We have a full block that is encrypted. It added these 15 values to the plaintext. It encrypted this. But when we decrypt with AES with the correct padding mode, it can remove our padding and we only get 1 byte out here. Okay, let's change the second one back to none. And let's go to the next one. This is ANSI X923. Let's have a look what now happens. And as we can see here, it added zeros to the end of our block. And then it added a 15 here, meaning that these 15 values can be removed. When we now change the second AES also to the ANSI padding mode, or ANSI padding, I don't want to print, I want to play, then we have again only 1 byte. Let's go to the next mode. So change this one again to none and this to ISO 10126. Press play. And here you can see that in this padding mode, it adds random data. So every time we restart this, we should see different byte values here because it always adds random data to the end of our block. But the last byte clearly tells us how many of these random bytes have to be removed. If I change the second AES also to the same padding mode and press play, then it removes the padded bytes from the last block. Now let's go to the last mode, and this is a 1-0 mode. Let's change the second AES again to none. And then we can see that it added a 0-1 to the end of the block and then only zeros. And if we change this also to the 1-0 mode, then we only get our 1 single byte. And one thing I wanted to show you is what happens, for instance, with this mode when we have a complete block. So no missing bytes in the last block. So we just copy this FF 16 times. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times FF. So this is a complete block now. And when we encrypt this, you can see that we have our block, our first block that we encrypted here. And then it padded an additional block here that starts with 0, 1 and then the remaining zeros. And this is because it always has to remove from the last block until it finds the 0, 1. So we have to add, or it added an additional block here that is only padding. When we change this here, of course, to the 0, 1 padding with decryption, it should remove this. And we only have our block. Yeah, and this is how padding in cryptography or in symmetric cryptography here, especially with the AES, works. In this video, you learned different padding modes. And now we had a look at these different padding modes. And you see how you can test these in CrypTool 2. Yeah, and this is everything I wanted to show you in this short video. I hope you liked it. If yes, please give a thumbs up. Also, if you did not yet subscribe to this channel, please do so. This really helps us to grow the channel and also to make CrypTool 2 more popular. Also, hit the bell icon to be notified when I upload new videos. So, thank you very much for watching and see you in the next video.